Hi, everybody. I'm Summer Ash. I am a astrophysicist and science communicator. And I'm super excited to be part of this Virtual Astronomy Live. Today, we have a really cool topic that I think most people wouldn't put together, but it's got origami and we've got space. And I'm joined by Dr. Charlene Morrow, who is a retired professor of psychology from Mount Holyoke College and a past chair of OrigamiUSA. And she's worked with NASA on several projects, including an educational project to inspire young women from underserved populations to go into mathematics and science. Hi, Char. And hello. I'm also joined by Keith Parrish. He is the observatory manager for the James Webb Space Telescope, which I am representing today.
Oh, nice earring.
Thank you very much. And JWST, for short, is run out of Goddard, NASA Space Flight Center in Greenbelt, Maryland. And Keith has been working with JWST in some form of another for over 2 decades now.
No, getting close, yeah, getting close to that.
Including the thermal design of the telescope and its all-important sun shield, which we will definitely be talking about today. So I kind of love that we're talking about origami, but with an engineer, a thermal engineer, and a psychologist. And I'm very excited to dive into this. But first, I just got to show you some geek evidence that this is a box of origami paper that I've had since elementary school.
Really?
That someone gave me as a gift. And I've used it, actually. I've restocked it a little bit, but awesome. I'm really excited to dive in today. So, Char, I wanted to start with you. As a psychologist, how did you get into origami and mathematics?
Yeah, great question. Well, it was a journey. And I guess without going into like the ancient history, I will just start with the fact that I came to Mount Holyoke in about 1986. And in part to run this summer program for young women in high school to inspire them to think about making mathematics part of their future plans. And as such, I was on a bit of a learning curve with mathematics, since, as you said, my background is in psychology. I do a lot of statistics, but not so much, straight on mathematics. I co-directed the program with my husband, who is a mathematician, so we did a lot of collaborating. And one day, I was in the bookstore across the street from our college, and I saw this book called Unit Origami. And I thought, wow, beautiful pictures of geometric models. Maybe could I hold one up just to give a sense of what kind of stuff was on the cover? Okay. Yeah. All right. So here's something.
Oh, yeah. So not little animals and frogs and swans.
No. And I don't want to sound demeaning of that or at all, because there's some amazing stuff. But what really caught my attention were these geometric models. And this is just a simple little 3-paper, geometric hexahedron. And it's connected together in a very clever way, which I did not invent, but I did fold. And I could say the rest is history. That I saw that book, I bought it, I decided to teach myself origami. I had not done any before. And I was using it to design a workshop for my students as a kind of alternative pathway to learning geometry, thinking about geometry in kind of like more hands-on way. So that was my inspiration, and I taught that. It was a 2-week workshop for the rest of the time that we ran our program until around 2009. So.
Oh my goodness! And how many students would be in the workshop each year?
Around 15, let's say 15 to 20 students.
Yeah, that's an amazing amount of students that have rolled through that experience.
It's true. It's really true. Yes. So that's how I got into both mathematics and origami. And I could tell you a lot more, but maybe they'll come up as we go.
Exactly. We'll get to that. And I definitely want to encourage both of you to ask each other questions if that feels natural. And so, Keith, for people that aren't familiar with JWST, before we get into the sun shield and details, I wondered if you could just give like a little bit of an overview of the telescope.
Sure. Yeah. So if anybody follows NASA and telescopes, most people are familiar with the Hubble Space Telescope. James Webb has been in development. It's got a long, storied history of development. I've been working on the program for quite a while. Most of that early development was technology development, and then over the last 10 years, we've really been implementing. So what James Webb Space Telescope is it's not a replacement for the Hubble. It's a logical successor, meaning that both ground-based systems and the Hubble Space Telescope have seen about as far into the universe. They still manage to use and extend Hubble's capabilities every year. But James Webb is intended to pick up that distance into the universe. It's significantly different in its architecture. It's not serviceable. It's not launched by the shuttle, which doesn't exist anymore. So it's really defined by two key things. Number one is it's extremely large. We have about 5 times the collecting area as the Hubble telescope, and we'll get into that in the Origami in a second because it is large. And the second thing is an extremely cold telescope. So it's an infrared telescope, where the Hubble is a visible light telescope. So it's extremely cold, and when I say extremely cold, I mean tens of degrees above absolute zero. We run the telescope. And then we also run all the cameras and the instruments at those temperatures. So what you're seeing here, you'll see that we use this large sun shield, which we're going to talk about in a second as far as origami and how large the entire observatory is. But you'll see that we use this large sun shield to separate out the optics and the camera system from the sun and the heat of the earth. And that's what allows our telescope and instruments, we cool them down to what we call cryogenic temperatures, which is about minus 450 degrees Fahrenheit, 60 Kelvin, whatever your measurement unit you prefer, but it's extremely cold and the size. So it's a really it would be an understatement to say it's an engineering marvel. It's been in development. I know people are frustrated at how long it's taken us, and we're almost to the finish line. We're going to get this launched next year. We actually have a working observatory. Every part is together. It electrically functions. We've tested out the optical systems down at the Johnson Space Center. And we're in final assembly, or actually final testing right now. We're getting ready to take the observatory through its final testing, which is where we simulate it to the launch environment, and then we'll deploy it. Once again, getting back to the origami, and then launch it next year. So we are very, very close to the finish line. Like I said, I know there's a lot of frustration with how long this is going to take, and it just seems to keep on going. But it is a technological masterpiece of an observatory. And I think the interesting thing about the science is that it's a relevant telescope. Over the last few years, Hubble has extended its reach, and the ground-based systems have extended its reach. So what's really happening in the astronomy community is the table is set, and everybody's real excited to get James Webb up there and to peer deeper. So really see those first stars and galaxies forming. I get real excited about exoplanet and atmospheres, which we'll actually be able to do. We can actually point this at planets and other solar systems. And so that gets into the technological challenge. And one of the big challenges is we have to fold this massive observatory up and get it into the rocket fairing or a nose cone of a rocket. So that's where we are. I've worked on it in a lot of different ways. And right now my focus is on launch day and the 6-month period after that. So that's really the commissioning period. And that's where we get it into orbit, get it checked out, and most importantly, get it unfolded. unpacked. So we're real excited about the next year as we get it into orbit.
Yeah, and to go back to the importance of the sun shield, I want to talk more about the fact that it's because, like you said, it's an infrared telescope, and we are familiar with infrared as heat, or because we're all giving off right now. We're all glowing in infrared, right?
Exactly.
But you need to also protect the instruments, not only because electronics run better when they're colder, but because you don't want the telescope to detect itself.
Exactly. I always tell people, if you went into the movie theaters and they didn't turn out the lights, you'd be really upset.
Yes.
So I say, hey, we want to turn out the lights, which is heat. So if we don't get the telescope cold, all those photons of heat in the electromagnetic spectrum, the infrared part of the electromagnetic spectrum, will just flood the camera. So if you take your iPhone outside and you point it at a bright thing, it's gonna blind it. So we don't want to blind it with its own heat. So that's the whole point of the sun shield, is to separate that cryogenic telescope from the heat of the sun. And then the other thing you'll see in this video right here at the end is you'll see that the sun shield is actually more than one layer. We actually have 5 separate shields. They're kind of nested together, and you can see them separating there. And it's that separation that allows this telescope to get so cold. If we only had 1 layer, it wouldn't get cold enough. 2 layers, not cold enough. 3 layers, not cold enough. So we add 5 layers, and you can see they're nice and stretched tight, almost like sailing a ship. And it's that tightness that lets all that heat escape before it gets into our optical systems.
Yeah, that's amazing. So Shar, before we jump back to the folding of the telescope, a lot, like you said, you got into more of the mathematical geometry, topography type of origami. What are the things that you taught your students about those? What kind of activities would you do, and what was the importance of those?
That's a really great question. So I will, can I show you a couple more things? Just some of these things really speak for themselves. So for instance, here's a model that I might teach my students. It looks very complex, right?
Absolutely.
But what's really interesting about this, and I'm not sure if this particular thing relates to aerospace engineering, but I don't know. It's surprising what relates to what. Something very basic, simple, like folding a piece of paper can, provide insight, like Keith was saying, about how to fold up things small and open large. Okay, well, this is a static item. This doesn't fold up anymore. It has 30 pieces of paper, though, that cleverly interlock. And it's got a lot of things in it about angles and about tabs and pockets. And I could just maybe, let's see, this one's kind of small, but I could unfold something here. I like to do this because people kind of feel like when you folded something, they feel like, no, don't ruin it. But one of the things I feel really strongly about, so you can see that, maybe you can't. Might interlock.
Yeah.
But if you can't fold and unfold something, then maybe you don't really understand how it works. And so
that's a great point.
A lot of origami is about making beautiful things, and there are really beautiful things. But my focus is a little more on problem solving. So I sort of feel like the interesting thing about it is making sure you understand how it's structured and how it works, and being able to make it again and things like that. So even something as simple as a box. So this is like a beautiful box. But my take on it would be, it's a hexagon.
Right.
What's involved in making a hexagon? How do you make it hold together? And one of the things that I really focused on with my students was I would give them like instructions rather than tell them how to do it. I would give them a page of instructions. Many origami people find it difficult to interpret those. Not everybody, but it's a bit of a challenge. It's the same challenge students have in geometry, and that is to interpret 2D pictures into 3D objects. At some point, every piece of origami, virtually every piece of origami, goes from 2D to 3D. And that is where it gets difficult to understand. It's hard to draw pictures of it. Oh yes, there's an object that some of you might have seen on the, I don't know if this showed up on the page, but this is a spinner. You can see this object. And maybe if I turn my camera on for a second.
Sure.
Let's see if this works.
So it actually spins.
It actually spins, and I have it right here. And let me see if I can, turn on my camera.
Oh, there we go.
Okay. Can you see it? All right.
Yeah. Wow, the whole thing spins. Ooh, wow.
Yeah, the whole thing spins. And I mean, it's kind of a marvel, really, when you think about it. I can turn off my camera now. Go back to me. It's just 3 pieces of paper.
Right.
And they're nested together. And there's not even really, it's only pointed because this little handle is squishing down on it.
Oh, right.
So
to give it the spin.
It just gives it enough to spin. And so action models in origami are really, really great. And there's one of our best known origami people is Robert Lang, who you might have heard of, because he has worked on folding space telescopes, and he has a lot to say, and he has TED Talks, and he's really interesting. Does a lot of very artistic things as well. And one of his talks is called From Flapping Birds to Space Telescope, folding space telescopes, right? So here's a flapping bird.
Yeah.
Awesome, right?
Right.
So there's a lot of engineering, I think, that goes into a lot of origami. And so if you look beyond just the object and you want to understand how things are structured and how they're folded and how they come apart and how they unfold, as Keith was just saying, like in the JWST, how things unfold are maybe just as important as how they fold. And I don't want to pretend to be any kind of expert here, but I know, for instance, a little more about airbags in cars. People might think that they're just stuffed into the compartment, but they're not. They're folded in a very specific way so that when you need it, it's going to unfold reliably and it's not going to get all stuck on itself.
Yeah.
And I was watching one of the videos that was shared, I don't know where exactly along the way, but about the JWST was it the sun shield or maybe yeah. And I was watching it and I thought, oh, it would be a disaster if that just like the materials got stuck to each other or they got caught on something or all of those things are so important. So I mean, there's some very simple things like I will show this. I think this sort of has inspired some sun shield types of things.
And that's one continuous piece.
What?
I have my own version of sun shield.
That is more relevant.
Not as fancy as that.
A little different shape, but But this is one sheet of paper. It's actually very simple.
Yeah.
Just a series of concentric squares, fan folded, and it folds down to a pretty small packet. Yeah. This does not fold completely flat, though.
Yeah, that's actually very, very similar to I have my own little paper model. It's definitely not as nice as yours, Shars, but this is the I don't know, where's the camera here? This is the concept for the gotta move it the right way. It's all delayed. So this is the concept. It's it's basically a kite. This would be one of the layers for James Webb, and what we did is we had to get this into the fairing. So all of our early designers and some of our chief engineers, and let me give a shout out to some of the very smart engineers who came up with these concepts. But that's really what they started with was how do you and really that's what we did. We did an S fold. You can kind of see this kind of comes in. We don't call it a Z fold because we don't want to hard crease the edges for the James Webb Space Telescope. And then when we got to this place, we got it all nice like this. And we said, well, what do we do with it now? Do we keep folding it? And what we did for James Webb was we just did 2 more folds to get it into this configuration, which is its launch configuration. And so we yeah, exactly. We could have kept on folding, but one of the practical limitations for flying one of these shields in space is getting the air out of it. So the more we folded it up, the more potential for trapped air. As the James Webb is on the rocket and riding, we're going from sea level pressure to vacuum. So if we don't get that air out, air pressure is a tremendous force that will completely destroy the sun shield if we don't get it out. So that was one of our big considerations was, we started with an origami concept, and we took it so far and we kind of stopped. And it was primarily to let the air evacuate. We wanted to fold it as little as possible in the end, because every time we do fold it, it's wear and tear. The more you fold it, the more damage you can do to the materials. And once again, it's all designed to unfold, sort of reverse origami when we get on orbit.
And I think anybody who has wanted to cut a sheet of paper in half and that person doesn't have scissors, and so what do? You fold it back and forth enough times. It just wants to come apart.
Yeah,
so you don't want to fold things too much if you don't want bad things to happen.
Yeah, we have folded. We're getting ready to launch next year, and we have folded our sun shield. And when we fold up our sun shield, it's 5 layers. They're all sitting on top of each other. So we have to fold them all together. We have folded it twice now, and we've just folded it again, and we'll unfold it one more time. So it gets 3 cycles of folding, and we really don't want to do more than that, because every time we fold it, we do have the potential to do that. So we don't hard crease it anywhere. We make sure that it's and it does take quite a while. I mean, one of the reasons we have taken a little bit longer than we had planned was the fact that when we fold it all back up, you talk about airbags. We have to fold it extremely carefully to make sure it's in its design, everything is in its place, because we're really focused on it unfolding correctly. So it takes quite a while to fold the sun shield up. As you can see from one of the earlier photos, it takes cranes, it takes lots of people, and it just takes an enormous amount of people to manipulate this large shield into place for launch.
Yeah.
So when it launches, it will unfold, and it will unfold itself, like robotically. But when you're folding it on the ground, is it a combination of machines and humans, or is it also robotically folding itself?
Yeah, all the actual mechanisms. So when it deploys on orbit in this direction, there's what we call telescoping booms, almost like a selfie stick.
Yeah.
They actually push these sides out. We disconnect all of those. We don't want them doing anything because they don't really work in reverse very well. So we actually almost all of the folding is done by people, and all of the actual hard mechanisms are reset. They're actually stowed also, and then we connect up everything to a system of cables, which actually does the actual pulling when it comes out. So yeah, it's all people to do it. So and it's quite an effort.
Do you have all of them added like the word origamiist or whatever to their business titles?
They really should, because we've been very fortunate that most of our folks love to work on James Webb, and really what we need to do is we have an experienced team who knows, they know the personality. They know exactly where the folds want to be. So it does have its own little signature, and they know it well. So absolutely, they should get their honorary membership in the club.
Yeah. Well, and because what's the material for the folding for this shield?
Yeah, so I think that's another one of our engineering challenges is we spent many years trying to find the right material. If you think about what this shield does, it has to be stretched tight. It has to survive for a decade or more in the really difficult environment of space over temperatures that can vary by several hundred degrees. And it's also being bombarded with protons and electrons, all kinds of nasty stuff that the sun spits out that we're protected here on Earth from, but James Webb is not. So we spent a lot of time developing a material, and we invented materials to see if they would work. We went to the mylar, the mylar balloons. We tried to see if we could use that. We actually took this and hit it with micrometeorites that hit it and blasted things at it. But ultimately, we found out that it's a plastic called Kapton that's regularly used in the aerospace industry. It was kind of right under our noses the whole time, but not exactly. That's a little bit of an understatement. There's a very specific flavor that's not really used readily of Kapton that we found had extraordinary strength over our temperature ranges. So we ended up using that. And then you'll notice in some of those videos that it's kind of got a purplish color to it. That's because we take that plastic and then we put a small layer of a metallic coating on it to give it the right reflective properties and the ability to survive for that long period of time. So ultimately it's a coated plastic, a lot like one of your Mylar balloons, but it's actually a Kapton plastic.
Yeah, that's really interesting because even within paper, and I know it's not made out of paper, but if you fold a lot of paper, you start to realize that there are many, many, many different kinds of paper, and they have different qualities.
Yep.
And some of them readily tear so this is like an old model that I've been playing with for a while. Maybe you can't see.
Oh yeah, the creases are wearing. Yep.
Yes, and you can see their little holes right where there are vertices here also.
Yeah, one thing that we have found with I got to get the camera. There's this weird delay. One thing we have found is right in this area right here, where we bend it up almost 90 degrees. We have reinforced that area because we've found over the years with some of our test articles that it would wear out where those folds are constantly being folded.
Right.
One of the things we also did was we started small. We started with paper models and then we started working with larger. We go to the hardware store and buy plastic sheeting, make another model and see how that folded. And as we found out, as we got larger and larger, because of the thickness of the material, because of the way it would slump in gravity, because we're trying to test this thing and build it in gravity. It's designed to be in space and in zero G. Is that we had to keep going bigger. We eventually had to build a full-scale test sun shield to really work out all the final details and how to fold it. So as you can imagine, the thickness of the material, as you went smaller, it just didn't scale very well. So we started small and we worked big. Another thing I want to point out when it comes to tearing, not sure if you can see this. You'll see these, looks like almost like a quilt pattern. This is actually from drawing. There we go. This is actually from one of our mechanical drawings. The sun shield itself is actually made of 4-foot wide material. You cannot buy material this wide, which is about 40 feet wide in reality and 70 feet long. So it's actually almost a quilt or a patchwork of seaming material. And the folks who, it really gets into like a seamstress kind of knowledge of how to cut patterns, almost like airbags. You have to cut them to specific patterns. So there's like 50 or so. I can't exactly remember. Each one of these layers is made of actually like 50 separate smaller pieces that have been seamed together. And that was actually another one of our challenges on, how do you actually connect all these little pieces up? Do you glue them together? Well, gluing turned out to be not a good idea because it would stretch and crinkle and there was mismatch in the properties. So a company in Alabama who actually seamed it all together for us, they had an interesting technique of sort of like welding it together Once again, that was one of our bigger challenges, is going from tiny models to something that's 70 feet long. And the institutional knowledge that you get with a lot of engineering, we really didn't have it. We had to sort of invent the institutional knowledge of how you actually build something this large around the cryogenic but as with your paper, tearing is always a concern. And those seams where everything is seamed together is actually, we call those ripstops, almost like a parachute. People, they don't want your parachute to tear, but if it does, it'll only tear so far. So that's really our sun shield. If it ever gets a large tear in it for whatever reason, the tear will stop because we've had built-in ripstops also. So there's a lot of really tiny features built into all the different layers to get it to that right shape, allow it to fold, get the air out of it, and then last on orbit for more than a decade plus.
Right. And in addition to the folding, oh, sorry.
Yeah, go ahead.
I was going to say, making things large, scaling up is also a big issue in origami.
Yeah.
And how do you support it? Because paper doesn't support itself at that scale.
Right.
Yeah.
That's been one of our bigger challenges, is how we deploy and test everything from the mirrors that, if you looked at the video, everything unfolds on James Webb. I'm talking about the sun shield a lot, but our mirrors don't fit in the fairing. Nothing quite fits. So we fold up a lot of things, and ground testing in a one gravity environment is very, very difficult because we don't want to help it. That would be cheating in the test. We want to try to negate all the gravity effects. And for the sun shield, you'll see in those videos, we kind of just deployed it and it kind of lays and flops itself on a table. And that's as good as you can do. We've even floated things out on water tables. Back in the day, we talked about flying things on the Vomit Comet to get into zero G. But yeah, ground testing has been a very big challenge for us. There you can see it's kind of flopped on the table there. This is actually one of our operations where we're folding it up. And you can see there's multiple cranes and systems that have to lift, and with people involved to do that.
And in the fairing too, like, it not only has to sustain the mechanical forces of being folded, but also of the launch itself, which is probably a pretty dynamic, jostling environment.
Yeah, exactly. I mean, when we fold it up, like I said, when we fold all 5 layers up, this is very thin. The actual sun shield is much thinner than this piece of paper, the Kapton plastic, about 1,000th or 2,000th of an inch thick. But when we actually do fold it up, it goes from being floppy paper to a very, very stiff structure. And so it's almost like, it's this. Let me turn the label around so I don't advertise. There it is. So it's almost as stiff as this aluminum can. It has weight, it has mass, and it has to be supported. So supporting it during launch, and there's 2 launch environments that we're really concerned about. One, the rocket shakes. If anybody watched the Falcon 9 a couple weeks ago with our astronauts, they had a nice, they described the ride compared to the shuttle. I thought that was fascinating. But yeah, there's a lot of shaking. The one thing that, that's one of our bigger environments is acoustics, just the noise of the launch. So if you ever heard thunder shaking your windows, it's very much like that. So the entire observatory will shake from the sound. So that's the test we're getting ready to do in the next month. We got the entire observatory. We're going to take it to a test, and we're going to hit it with speakers. We're going to shout out it really, really loud, and we're going to shake it on a big paint shaker table to make sure it all holds together. Now, fortunately, the telescope and the spacecraft and sun shield have already been through those tests and survived and did well. Now we actually have everything together, and we're going to do it all over again. So yeah, that's where we are. So yeah, the rocket. I always tell people the sun shield has been an engineering challenge because it's sort of got 3 buckets of things. It has to be out and do its science mission, which is to protect the telescope and get it cold. It has to deploy, which is another bucket of challenges. And then the 3rd bucket of challenges is surviving the ride to space. And so those 3 things together. And like I mentioned a little bit about the institutional knowledge that we had to come up with, and NASA's used to moving big things. One thing we're not really that good at is moving, and something we had to figure out how to do is move a big, delicate telescope. So you can see some just some images here of how we get this telescope from around the country, because it was at the Goddard Space Flight Center in Maryland. It was down in Texas. Now it's down on the West Coast. Eventually, it's going to go to French Guiana in South America. But we use this big shipping container that barely fits into that C5 Charlie provided by the Air Force. And eventually we put it all on a ship and it goes to the Panama Canal down to the, so just moving this around was kind of a new thing because it's so delicate. You say, well, it's delicate, it has to survive launch, so it can't be that delicate. But actually the way it moves and how it's subjected to different environments in that moving process is a little bit different than a launch. So we have to design it to account for everything.
Yeah, but you make a good point about how the properties of it unfolded are different from it folded, as far as like what it can
exactly. Yep, it's a completely different animal when it's folded up.
And Char, I remember you showed us at one point like that you could have, well, first of all, origami paper itself is so thin, but you can fold it and do things with it that can make something stable. So I remember you had something that almost you could sit something on top of it, but it was really made of a couple different papers folded together. Yeah.
Or maybe it was
one piece.
One piece.
Yeah.
Oh, wow.
Yeah. So this is just a basic corrugation. You've heard of corrugated cardboard.
Sure. Yeah, that makes sense.
So this has a lot of structural integrity. Like, actually, can I turn my camera on again for a second?
Yeah.
Okay. Because let's see here. A couple of things about this. All right. So one thing is, yes, there we go. So it has a lot of structural integrity. It's about maybe a ½ an inch high. I can take my cell phone, for instance, which is fairly heavy, and just set it on top, and it doesn't collapse. So you're starting to see like some ways that you can create that sort of thing. But the other cool thing about it is if you press anywhere.
Oh, right.
It's kind of connected. Get my hand out of the way. It's connected in a way, like sort of
distributing.
That yes, it you move one spot, it moves the whole thing, which is kind of cool. Just from a folding paper. It's just basically like B folds, alternating mountain valley. And then it's got some vertical folds that alternate in between. And this is like one of those, it folds up pretty small considering.
Right.
So here it is.
Yeah.
Here, let me turn my camera off so I can hold it up, not on a white surface. Anyway.
Yeah.
So I folded this one into 1/8 inch, 1/8 of the paper width sections. That's pretty small compared to what it looks like. And this is related to the sun shield that, or rather the solar array that has, I think, already gone up into space. That is invented by a Japanese aerospace engineer. And it's called, in fact, his folds are called Mira Ori, which means fold.
Okay.
And they're rather famous. This isn't not it, but it's maybe related. But I could show you something more similar.
Yeah, I mean, as all these structures get larger and larger, just all these folding techniques are, they're almost a necessity. So you have to,
How else are you going to make it small?
Exactly.
Right. How else are you going to get it off of the Earth and into space?
Yeah, but here is more like a Mira Ori.
Ooh.
So you see this one not only folds into a strip,
Yeah.
Actually, it's not
in both directions,
but it also folds down, and so that's
Yeah.
a really small.
I think for
and you can see how efficient it is.
Yeah.
Because I can just grab two corners of it.
Right.
It's
And
a bit. It's a bit trained.
Yeah,
you have to train the paper. Yeah. I'm sorry. What?
Oh no, I was saying for James Webb. I mean, a lot of those techniques were, if we only had a single shield, we would definitely employ even more of those techniques to get it a little bit smaller.
Yeah.
The fact that we have 5, so I know there's really cool stuff coming along like Starshade. They're really going to benefit from a lot of these techniques on how to package them up because they're really large structures.
Isn't the telescope itself also has a folding structure, doesn't it?
Yeah, so the telescope is a hard structure. So we fold, there's 18 mirror segments that make up the main mirror. Yep, just like the earrings there.
Awesome.
And 6 of the 18, we drop down like almost like a drop leaf table, I call it. They drop down so we can fit those in. We call those the wings. They kind of do one of these things. And then there's a tripod, sort of a tripod assembly that holds what we call the secondary mirror. And that's a really interesting folding. It's almost looks like it's sort of like an insect as it unfolds because it has two legs that don't bend at all. And then it has a third one that has a big crease in it. So that's what we actually get our secondary mirror out. So the telescope, but that's all hard structure. So it's still origami technique in that we're trying to pack it up as small as possible into an interesting shape.
You hinge it rather than fold it, I think.
It's mainly hinged. Yes, exactly right. Yep.
But there is this little model that I believe, and I don't know if it's the telescope for that, but there's this model that does this.
Yeah, that's close to what the Starshade is.
Yeah, that's the exactly right.
Okay. Yep.
Yeah, it's a spiral in the center.
Yeah.
Yeah.
So every mission's got a unique set of requirements. Like I said, for James Webb, it was about getting cold. The edges around the sun shield have to be controlled pretty tightly. But when you talk about something like a starshade, and for folks who don't know, a starshade is an occulter that will let telescopes look at planets around other stars because the starshade will block the light of the star and shade it. And that way the telescope can see this little faint pinpoint of light that's next to it. So that's what these starshades are. And they're talking very large size starshades. So they can actually, imaging a planet around another star. That's awesome. I mean, but for James Webb, our edges have to be pretty closely aligned, kind of like an inch over 70 feet. We don't want layer 1, the one that's closest to the sun, peeking around the corner and seeing the telescope. That would be bad. We don't want any of the layers peeking around the next layer and heating up the next layer. So all of our edges are tightly controlled. Another feature of the sun shield, and my little paper model here sometimes does well. You'll see these little catenaries, these catenary shapes. I don't know if you can see that or not.
Yeah.
The catenary that you see there is actually a cable embedded into the shield. That's where we pull on it. We pull on that catenary, and that's what gives it this nice tight shape. Right. Now the edges of the sun shield are another cable, and we don't pull on those as tight because that's the edges we're trying to keep precisely aligned. So we pull them a little bit, keep them nice aligned, and then we use that catenary to pull the rest of the sun shield tight. So that's what I get into that third bucket where, once it's deployed, it's got to do a lot of things, and pulled to the right shape is one of them. And then say then you hold it all back up.
That's one point I wanted to make about the little, starshade. So here's one made out of cool paper.
It's got a good optical illusion going.
Yeah.
This started as like a toy.
Yeah.
It's called the flasher in the origami world. And it was invented, I guess, co-invented by Jeremy Schaefer and Chris Palmer. But
Okay.
I don't think they were thinking, oh, I'm going to make this and it's going to go into space and be a star shade.
Right.
So it's sort of the surprising usefulness and connection. And when you really think about it, getting back to the origami for a minute,
Yeah.
there's so many things around you that fold up. Everything folds up.
Mm-hmm.
You know, there are people who study protein folding in biologically.
Oh yeah, yeah.
There are stents, medical stents that, I mean, they're not paper when they go into your body, but you know, they were invented using origami.
Using origami, right? I've read that. Like the box blow up design origami led into the heart stent folding.
Yeah. And just, you know, so many things.
Mm-hmm. Yeah, I know another application that's out there is solar sails. You know, for very large. You know, where you actually use the photon pressure of the sun to actually propel you through the solar system, or even, you know, there's some concepts out there that you can get enough velocity to leave the solar system. So very large. You need solar pressure, we call it, is very small. It's
right.
So if you had a big enough piece out there, you know, almost like it's literally solar sailing. I guess that's why they named it that. Sounds like a good name. But you know, another interesting thing about James Webb when it comes to solar sailing is our sun shield is a really bad solar sail. You would never use this concept to sail, but it's big enough that it's got enough solar pressure on it to actually move us around in our orbit. So our engineers who work with our orbital mechanics and our attitude control engineers, they actually have to take in that solar pressure that hits us constantly and take that into account when they calculate our orbit and adjust our orbit to make sure they know where we are. The other thing is you'll see in this picture here, you'll see a little, it's not really a flap, but if you go to the left side of that photo, there's a line coming down.
Yeah.
That's actually what we call a trim flap. Yep, exactly. Thanks, Dash.
Oh, no.
No problem.
Yeah, so on the back of this, we actually deploy something called a trim flap, and it does exactly that. It trims out our solar pressure because what happens is our center of gravity of the observatory is not exactly lined with our center of pressure. So what happens is the sun is trying to flip us.
Right.
The pressure on that sun shield is actually trying to flip us over. So we use this little flap to sort of balance that a little better. And what that gives us is it gives us more mission life, because in order to counteract that solar pressure, which is what solar sails like, we have to use fuel to get rid of all that what we call momentum buildup. So by putting that little flap there, we're actually extending our mission life because we don't have to use as much fuel to counteract that solar pressure. Bingo, right there, you saw that flap come out. So yeah, that's our counter, sort of like our counterbalance that we put out there to balance out that solar pressure.
Yeah. I did a little bit of a deep dive, just like looking into the history of origami, and I never even stopped to think when paper was invented, but it was about, like, I guess in the second century by the Chinese. And then it said, origami's been going on in Japan since like the 6th century, but like ceremonial at first and religious, and then coming into like all this popularity of the animals. It's just so wild that it sort of started off much more of like an art, and we found all of this mathematics within it that we're now applying to all of this future technology.
Right. I don't know if we have the final word on the history either, because I know for one thing that the Masu box, which a lot of people have heard of, it's a very traditional box that is sort of half as high as it is wide, basically. It was used as a standard rice measure. So I don't really know what year that came in, but I mean, I think, you know, we could say it's a few hundred years old.
Yeah.
So there might be things that we could, if we had enough history, recorded history, we could uncover that has gotten a little bit lost along the way. And I just wanted to mention also that there is a kind of European,
That's what I was going to ask you.
yeah, history of origami that, you know, this is sort of recently being explored by people, but it appears that it might be a little bit separate, a little bit independent.
Right.
And there's like a whole interesting bunch of napkin folds that were invented around the end of the Middle Ages, when people started, you know, sitting down at the table and using plates and utensils and napkins.
Yeah.
And there's somebody who's written a history of this, which is really interesting, very intricate folds. So even using something not paper.
Right.
Yeah. And when you think about it, clothing, just any kind of textile, has folds in it.
Yeah.
I'm like a terrible folder of all my clothes. So.
Well, that's a whole different subject. But to wear them, you know, and to wrap them. And if you look at the way that sari is folded in India,
absolutely,
there's a certain pleating process that happens.
And some of the ceremonial, like the head wraps.
Yes.
Yeah.
Hey, Char, do you, for your patterns, do you start with a hand sketch, you know, math, or is there any software involved that you use, or, you know, when you're coming up with something new, is it typical?
When you come up with something new, I would say that people have a lot of different ways to do it, but people will mess around with paper and using sort of folding techniques they know and looking at the way things could work and making, if you're inventing a new animal, making appendages and then kind of backfilling. Sometimes it's very hard to diagram what you just invented.
Yeah,
but then there is a whole line of software too.
Yeah, I know folding James Webb as far as the, you know, compared to origami, like, you know, some of the intricate patterns looks rather simple, but, you know, one of our first designers who actually architected most of the folding design, you know, we were really trying to, or a lot of the team was trying to force the sun shield to do what they thought it should do. And he was really he was really advocating to, you know, let's see what it wants to do as a material and how it wants to fit into certain places. You know, he had sort of a statement. He said, let's let the hardware tell us what it wants to do, and then versus trying to force it. So a lot of the little, if you really dove down into some of the intricate folds that we can't go into here, and it's hard to show them. It's really because he advocated for, you know, a little bit of trial and error, but it's like, hey, it wants to fold this way, don't fight it. And that's really some of the nuances is related to, you know, to his, you know, to his advocacy of that technique.
Yeah. Well, that's really interesting. And I mean, but there are some, I'll say, laws of nature about folding. So if I could just say really quickly a point here about, like, there's a reason why this folds flat.
Right.
Because there's a rule about where folds meet. And if they meet in 3 mountains, 1 valley, or if there's a difference of 2 between the mountains and the valleys, it will flat fold. Here's an object here that does not flat fold. I cannot press this down to be flat, because if you look at the intersections here, they violate that rule, and it will not flat fold.
Exactly.
So there are certainly things like that. And there are programs that people use to investigate things with some of that built into it.
Right.
Yeah, I watched one of those TED Talks by Robert Lang. And I think I remember him saying that there were like four basic laws of mathematics or of folding that kind of explain all of origami.
And it explain a lot.
Yeah.
Yeah.
We do actually have a mirror origami model now of your earrings. you can go to our website. Let me see. I think if it shows you here. I don't know. It's all blurry. Anyway, it's www.jwst.nasa.gov. and it's easy to navigate that site. But under features, you'll see a plan form model of our 18 hex mirror, and you can print that out for our audience. They can get themselves some origami paper. And I don't know if you've tried it yet, Char, but
I have not. I'm going to
take a stab at it. So I didn't do it because it was 16. It said it needs 16-inch paper, and got to go hunt that down somewhere. So,
before we go to Q&A, Char, you've done some other work with NASA and origami. Can you just tell us a little bit about that? Was it with the different?
Thanks for mentioning that. So just in the past year and a half or so, I've been working with the Chandra X-ray Observatory with Kimberly Arcand there, and looking at an educational project that could help give some insight into some of these ways that things fold small and open large. And so we've designed several programs, folding lessons, so to speak, with some interesting questions associated with them. And they're up on a website now. They've just been put up. I think I was told by someone that after this program is over, there's going to be a page of resources. Is that true?
We can go and happen for sure.
Yes. Yeah. And so you could go there and you can learn how to fold this.
Yeah.
You can learn how to fold the flasher, and you can learn how to fold
the tiny little star.
Yep, the tiny star. And there's one other thing on there that this one, the hyperbolic paraboloid.
I think I found it just by Googling Chandra and origami.
Yeah, and there are videos.
Yeah,
videos that I did.
Oh,
so you can see me teaching how to fold those things. If you think they're cool, they take a little time, but they're not super hard. And then there's some sort of questions relating to that. And then they have some other resources too. So, I think that should be, I'd love to hear any feedback about those because they're just newly out.
Mm-hmm.
Oh, cool. Yeah. Well, so speaking of...
Can I give one other thing? If
absolutely.
You love origami, our organization, OrigamiUSA, is having an online convention starting at 3:00 tomorrow. Not too late to register.
Oh, wow.
You can even register during it. It's like $30 from 3:00 tomorrow all the way through Saturday. And Robert Lang is giving one of the first lessons.
Oh, wow.
Yeah. And there's already close to 1,200 people registered for it.
That's amazing.
So we're excited about it. And if anybody wants to join that would be, I think, really a lot of fun.
I was just going to share one more thing with you that I like to do if I go, usually at coffee shops. Apparently I've seen, they always have like a little tip jar, or back in the day when we were allowed to go to coffee shops. But as I mentioned, I learned some origami when I was, growing up. And I had a student in my school from Japan, Kenichi Ono, who taught me those little rocket ship.
Oh, the dollar bill rocket ship.
Yeah, so I always do it and leave it for the coffee shop. But that's the one, I have the muscle memory and everything for it, because for years I never folded it. And then all of a sudden I remembered it and I was able to make it happen again.
Yeah. So, Star, are you a wicked paper airplane maker too? Or
me?
Not at all. Are you,
now we're going to get into some embarrassing things like I don't make paper airplanes, because I am totally into the more geometric stuff. Yeah. I love boxes. I love just purely geometric things. Yeah. I actually do a lot of origami that is based on different mathematical ideas to kind of demonstrate a principle. I'll show you one thing. So here's a cute cube. It's 3 colors. So the question you can ask is, how many different ways can you arrange these colors on the edge of this cube? Because it takes 12 pieces of paper to make it.
Wow.
How many that would be totally different from each other? So that's the kind of thing I sort of, and the answer is a surprisingly large number. So that's really kind of my thing.
I guess for Daz, if you lose me, it's because we're getting ready to get hit with a thunderstorm. So.
Oh, geez. Thanks for the heads up.
Yeah, I was just going to say, I'm going to stop.
Yeah.
I'm hogging you guys and let some of the listeners and viewers ask some questions that Das is gonna run.
Oh, I can jump back in over here. Do I have my name right? Yeah, okay. My name's
Yep.
right. I can't get my own name correct. While we were going through that, that was all really cool to listen to. Chat, what did y'all think about all the discussion there on James Webb and origami? And there were things that I had never even thought of before, like a mathematical or like a rule that says if they meet this way, then they'll fold up. But if they don't meet that way, then you won't be able to compress them like you held up there, Shar. I had never even thought of that before, but it makes perfect sense. So we do have some questions here to go through. We've been gathering questions the entire time here. Do y'all still have a little bit of time so we can do some Q&A?
Yes. Oh, absolutely.
All right. I mean, the show is actually timed for another 26 minutes, so I knew the answer to that before I asked. I just, engaging in conversation. So
always only ask questions you know the answer to.
Yeah, exactly.
Oh, no. So that's so boring.
Let's pop over to Q&A mode really quickly. And just really quick, for the people in chat, if you have a question for us, you can ask it right here. That's one of the cool things about the live interactive shows. It's not like, oh, just a pre-recorded video sort of deal. If you have a question for us right now, since we're live, start your chat line with the word question. And if you say question and then you type out whatever your question is, it goes into a special queue over here. I've already got like 20 questions queued up, and I'll be able to get that. We might not be able to get to every single question because we could sit here and talk about origami and spacecraft for hours, right? So do a question there for us, and I'm going to jump right in. Shar, you must be reading ahead or something, because one of the first questions that came through was whether or not OrigamiUSA has any online events. And like you said, tomorrow there's an online event, right?
Tomorrow through Saturday night, actually.
Through Saturday night, no kidding?
Yeah, the event starts tomorrow at 3 with a little intro, and then then Robert Lang is teaching a class.
Yep.
And there are some live chat interviews. And then on Saturday, there are going to be 5 more classes taught by pretty well-known origami people.
Very cool.
Throughout the day.
Very
cool.
Much
that's what we're doing all day.
So it was literally one of the first questions that jumped in was, oh, that sounds really cool. I want more online origami content. So there you go. You can have some live interactive.
And go to OrigamiUSA.org. We have Origami Connect classes. So those are live online classes taught by origami people that you can sign up for, and you can get all that information. There are local groups that, because we're meeting, I run a local group here in Western Mass where I live. And because we're online now, we got people from all over the world. You can join that.
Gotcha. So cool. Y'all, one of the mods, get a link to the OrigamiUSA thing in there, because this is one show we're doing today, but there's going to be all sorts of other cool things that you can participate in. Thank you so much for sharing that with us. So I'm just going to go through some questions, and we'll rapid fire some of them and see how many of these we get through here. And they'll be about origami. They'll be about James Webb. I'm just going to sort of pick and choose. So again, y'all, if you're watching at home and you have a question, start your chat with the word question for us so that it gets into the queue here. So here's one. Let's see here. This was a question from Godzilla Train. Screen names, right? And it was, how do you assure that the James Webb origami will open in a microgravity environment when you're testing it on Earth? So do you simulate it in some sort of zero-G? Have you tried to unfold a James Webb in the Vomit Comet or something? Do you support it so it's sort of neutrally buoyant underwater or something like that?
Yeah,
how do you do that, Keith?
If you saw those images, you'll see that the membranes, or what we call the layers, we need tables just to hold them. There's no way that we can sort of float them or mimic zero-G. Now, for the big mechanisms that pull and push on those membranes, they're offloaded with counterweights.
Okay.
A very intricate counterweight system will offload the gravity pull of them in our test lab. So we do a very good job. Like I said, you don't want the counterweights to help it.
Right.
Kind of trick you into a good feeling that it works really well. But then again, we have to get the gravity out of there. And then the other big thing about this is all of our work is supported by analysis. So we have very interesting what's called Abacus models that actually can simulate all the forces, the gravity loads, the zero-G environment. So we always contrast what we're seeing on the ground, make sure if our models can predict what we do on the ground, we're pretty confident our models can go up to a zero-G. So
gotcha.
and we use supercomputers to compute those forces in a 0G.
Gotcha. So you think about it, you run the math, you run the numbers, you do it on computer, then you test it as well as you can, trying to support it to get it to 0G and that sort of stuff. It's really sort of like they did the flying bedstead. Remember during the Apollo program, they had that lunar lander trainer, and the lunar lander trainer needed to simulate
Armstrong's favorite.
Yeah, exactly. They needed to simulate 1/6 gravity for the moon, so they had a jet engine that held 5/6 of the gravity.
Counterweight them, the counterbalance.
Yep, exactly. So you do everything you can here. We have gravity; it's Earth. That's how it works. But you have some cool engineering ways that you can sort of.
You'll notice, people have always seen the astronauts in the neutral buoyancy lab, which is a big swimming pool down at the Johnson Space Center, so they can really get a feel for 0G, working in that environment. So,
absolutely. That's a great question, Godzilla Train. Thank you for that question. So here's another one, and this is space a lot, so we have a lot of space-related questions here. This is from DYU89, and they asked, how much shaking do you anticipate on launch, especially with the solid boosters used at liftoff? Is there anything dampening it? Like, is James Webb driving on a big shock absorber or anything? Or have you tested shaking James Webb and then see if it still unfolds cleanly?
Yes, we've done that. So we launch on an Ariane 5,
right,
which is provided by our European partners, and the Ariane 5 tells us how much the Ariane Spas, which is a company, they tell us how much to shake James Webb in our testing program.
Okay.
So they give us a specification for frequency and forces, and then, like I said, we have equivalent. We call it shaker tables. But if you ever go and get paint shaken up at the store, it's a lot like that. And we've done that. We've done that to what we call qualification levels, which is Ariane Spas says the rocket will shake this much, so we shake it just a little bit more.
Okay.
And we've done that with all of our components. We've done that with the sun shield, with the spacecraft. We've deployed it after we've shaken it. And like I said, in a couple months, we're going to take the whole observatory together and shake it.
Gotcha.
So yes, we do that.
All right, good deal. Here's one about origami. So this was from Musigamist, and the question was, Shar, this is probably, this one. How do you deal with the creep from the layers as you fold it? So when you're folding origami, it sort of gets out of alignment. I don't know what the right way to say it, but is there a special trick you can use? You just get used to it?
Well, paper creep is an official term.
Really?
So this person knows what he or she is talking about.
Yeah.
And it happens when you try to, maybe I can sort of show you with this little thing. It happens when you fold paper over and over again, especially if you're folding it one way and then another way and then back again the other way. And because paper has thickness, as Keith, I think, was saying about the material, it can look very, very, very thin, but it doesn't take long of folding it over before you get a lot of, it can't go around itself because maybe your diagrams in your head are ideal.
Right.
And you want to fold it over and over and you want to make the edges meet, but they can't because they're being forced around an edge, and it takes up some of the paper, so it can't reach the top edge.
It's like the more thickness of paper that you have in each fold, the more radius it has to fold around, and that sort of steals some of your paper, right? Does that sort of make sense?
Exactly. I think that's a great description of it. And so what you do about it really depends on the model you're making. So if someone's teaching you a model, they may say you really need thin paper for this. You can't make this out of thick paper.
Right.
And that's going to probably be the main reason, because you're going to be folding it over and over and over again. And after a while, you're going to make small folds through many layers of paper. It's just about impossible.
Yeah.
So someone like, there's a very well-known paper maker named Michael LaFosse and also Richard Alexander. The two of them they have a paper studio. They're both really well-known origami artists, but they also make paper. So people will order, like, I want a really thin double-sided paper that will withstand folds and won't rip. And so they'll go to work on that and, try to work on the properties of it to invent that sort of thing.
That's almost what y'all had to do with James Webb, right, Keith? You had to get a company to make special material for the sunshade, and I guess that had to be a certain thickness and that sort of stuff, right?
Exactly. Yep. We specified all of that because once again, I don't know. I hate to go back to this little paper model, but I will because Char hit it on right at this fold right here. Because we folded it in, it's about 70 layers thick there. So 70? when we do that one big fold, we have 70 layers, and guess what they want to do? They all want to shift.
Oh.
They all want to move to a different place, and you get this kind of weird thing you battle. So yeah, paper creep shape. Yeah, we see it exactly.
So that's
like
that
a cross fold. Yeah. By the way, I'm not sure if you have where a paper is orthogonally has two pieces folds on. We call it a cross fold in James Webb parlance, but our cross folds are where we get the maximum stress and where our tears can happen. So
yeah, and it can start to crimp inside there, like at that even the U shape. Yeah. So it's little wrinkles. Yeah. Yeah, it's a great question. I mean, it's one of the things you have to really problem solve about if you're going to do origami.
Exactly. Yep. Practical problems. Yep.
Absolutely. So here's another. I'm just going to get some more questions in here. A Broken 44 said, I heard the mirrors are very finely aligned and a deviation would ruin the captured picture. I imagine the strong vibrations during launch would mess with the finely tuned instruments. So how does the telescope check itself? How does it compensate for maybe getting shaken a little bit during launch, and then does it recalibrate itself to figure out exactly how much it needs to unfold? Or how do you deal with that?
So I mentioned that 6-month period after we launch called commissioning. So if you looked at those mirrors, there's 18 of them. They're actually 18 separate mirrors at launch, and we do something called snubbing them. So we push them down really hard against a stop.
Right.
That way, when they launch, they can handle the vibration. When we get them in orbit, we do something called wavefront sensing and control. So each one of those mirrors has a series of mechanisms on the back of it that let it push and pull and tilt and turn. So over a period of that 6 months, as we're cooling down to these cryogenic temperatures, we have some of the world's best optical engineers. They're going to look at stars, and they're going to use reference stars, and they're going to align using these very precise mechanisms on the back of the mirrors to align them all. And what you'll get all 18 mirrors acting as one big mirror. We call that wavefront sensing and control and alignment. So yes, we had to be able to do that on orbit because there was no way for us to align it on the ground, have it survive launch, and be a great optical system on orbit. So that was implemented in the design.
Gotcha. So every one of the mirrors, as opposed to having one big mirror, it's kind of hard to fold one mirror, right? But another thing you get, because you have all the little 1, 2, 3, 4, 5, 6 hexagons, is you're able to tune each mirror a little bit, each segment, I guess.
Absolutely, and that's the beauty of that design.
Yeah.
Because we couldn't build one monolithic mirror. If you look at the Hubble Space Telescope,
like Hubble,
it's a monolithic piece of glass. We couldn't have done that large. And then even the ground-based telescopes, you go out to Keck in Hawaii, you'll see their hexagonal mirror segments, and they've really pioneered how you align those hexagonals together to act as one mirror, and that's our goal. So that's a rather intricate process on orbit, and it takes us quite a while on orbit. But and there's computer models running on the ground, and it's a really interesting process. But that's how we get to orbit and actually have a working telescope.
God, that makes perfect sense. I mean, you have to launch. As it turns out, it takes a lot of energy to get off the surface of the planet and up into orbit. So you're going to get shaken around. You have to deal with that. And so we
go from 0 to 25,000 miles per hour over the course of 10, 20 minutes. So those forces are it's like, let's build this great telescope.
Yeah.
Well, now let's hurl it into space.
Space.
It's non-intuitive, but there's lots of space telescopes that have successfully launched. So. Good question. Another great question.
That was a great question. Yeah, this is the thing. Like, there are a bunch of really cool people in chat, and they have so many good questions. There's no way we were ever able to get to all the questions, so I'm continuing to go through.
This is the fun part.
Yeah, it really is. It really is. Really quickly, how far or fast will James Webb go? So that sort of ties into what you just said, 25,000 miles an hour. How far away from the Earth is it going to be?
Yeah, so we're putting it in a special orbit called Lagrange Point 2.
Right.
There's actually an orbit around that place, so it's a million miles. So
about a million miles.
The moon's 250,000 miles, so we're about 4 times the distance away from the Earth as the moon. That's a unique place. So we're not going around the Earth every 90 minutes like most satellites. We're actually sort of in a solar orbit. So as the Earth goes around the sun,
right?
I can't even. As the Earth goes around the sun, James Webb sort of gets dragged along by the gravity of the Earth, and it's this unique mathematical, a lot of mathematics here that Lagrange discovered. Every two-body system with gravity has these Lagrange points. Where gravity does this weird interplay. So we like that because what that does is over the course of a year, James Webb can observe the entire sky.
Right.
And it lets us keep the sun shield between the Earth and the sun and our telescope at all times. So we like that Lagrange point too, but it is 1,000,000 miles away, so it's pretty far.
I was going to say we need Char to fold us an origami telescope and some origami Earths, and then we can have models to actually hold up.
Oh yeah. I need the 7th grade science project with the planets.
Give me a couple days.
Give you a couple days. Wait, right? I mean, we have 10 minutes left. You're the origami expert. Like,
yeah, I'll have it done right away.
Exactly. She just goes shh, and then holds it up all of a sudden, like in the cartoons. Really quickly, how many people have been involved on working with James Webb? The number's always bigger than people think, so I'll ask that one real quick.
Yeah. At the magnitude of the program is it's amazing. I mean, we're an international program.
Right.
We have our foreign partners, European Space Agency, the Canadian Space Agency, and NASA. And then even within NASA, we have our industry partners, our big companies that can do specific things. All the names you're familiar with in aerospace. And then we have our scientific community out of our universities. Yep. So over the course of its development, you're really talking thousands and thousands of people in Europe and Canada and the United States. Right now, we have a large team preparing for launch and operations. So it's amazing. I mean, you're talking hundreds and hundreds of U.S. companies that have built everything from washers to a company, Brush Wellman in Utah, that has mined our beryllium and made these beautiful mirrors for us.
Really?
To a company in Delaware that puts the gold coating on them. So it truly is. There's no way we could build James Webb without an international engineering and scientific, everybody bringing their skills to the table when doing it. There's no way even one company in the United States could do it. So it's a very big program. It's one of NASA's most ambitious missions ever. And it has, it's basically required every ounce of industrial knowledge to build this beautiful machine.
Right. So that's another great question. So
great
Amy,
question,
there you go. The answer is a lot of people, a lot of companies all over the world to make this thing happen.
Some of our really good videographers, which our videography team, which made a lot of these beautiful videos that you're showing.
The time lapses are awesome. Tell them I said.
They're putting together a documentary on. At least they plan to do a documentary on all the different companies, tiny little companies that only do one little tiny thing to big companies to really give a shout out to the capabilities of our industrial and our technology capabilities.
Gotcha. So I've got two. I have like 20 more questions here. These two sort of go together. This is from Slink and Godzilla, or from NASA Spaceflight actually. How do you keep the heat from causing the paper to hold its shape? So as thermal things change, I guess as the thermal environment changes, sometimes it almost like irons it like a shirt. And so if you imagine you fold over the sleeve as a shirt and then you iron it, you apply some heat to it, it gets that crease in it, right?
Yeah. So I mentioned earlier to those catenaries that are always pulling. And then at the end of those cables that are pulling are springs.
Okay.
So as once again, this is plastic, so it doesn't shrink a lot. Once again, we were trying to find a material that didn't shrink a lot.
It's like space plastic.
Expand a lot. So we use springs to actually counteract the shrinking and the expansion due to these thermal effects to keep that nice flat space. So we call them negator springs.
Okay.
At the end of each cable. So as the temperatures change, these things, they kind of go in and out, but they always keep the same tension, and that's what allows it to stay flat.
Gotcha.
Another good question. Wow.
Again, you engineered it so that it would.
but people are really hitting on the engineering considerations that go into this that you may not think about.
Yeah. So this is somebody who knows about it. Apparently, at one point when you were testing it, the Sunshade Tour, was that like a prototype you were working on or something, or the
No,
actual flight?
We've torn the flight one, and we were ready for that. So back in the day, the company that made these membranes, we also had them make patch kits.
Really?
Yeah. So we don't want it to tear during testing. Obviously, that wasn't our plan, but we did get tears. Places that we saw were getting ready to tear, we went in and reinforced it. I don't know if you remember those patches you put on your kids' pants, or my parents put on my pants.
A tire or something, like a tire kit for your bike?
Yeah, so we don't want it to tear, but that's why we don't like to do, that's why handling it on the ground is so slow and careful and tedious. But we have had tears, none of them catastrophic, and we did anticipate it, we prepared for it, and we patched them. We already had patch kits, and we had the vendors come in who had the knowledge of how to do that. So, yeah, don't like the tears.
Don't like the tears.
Sure, but it does happen.
Yeah, sure. How do you deal with that when you're folding origami? Origami doesn't cost $1 billion, right? It's a piece of paper. But if you've spent all this time folding a really complex shape, and then something goes wrong, it gets a little tear in it, or it's just stress, like you've had it on your desk and you play with it all the time and eventually wears out. How do you repair origami? Do you just fold another one? Do you like a little piece of tape on it? Is there any tricks?
Well, a couple things. I mean, you can use the crumple technique.
The crumple technique.
Meaning I'm done with this.
Circular files.
The circular file.
Yeah. Actually, I'll just take a little diversion to say that one of the activities that, and this doesn't relate to your question exactly, but one of the things we have as an activity is looking at crumpling versus folding, just to investigate what really is the advantage to folding things versus crumpling them.
Right.
And so I think that's an interesting question, but okay, let me come back to the question.
Sure.
I mean, you could take a number of different approaches. It depends how valuable it is. And, you know, you could, God forbid, use tape or glue to patch things if it isn't front and center. But paper is very tolerant of a lot of things. But when it breaks. And so you could decide that you're going to use it as a problem-solving opportunity.
A problem-solving opportunity.
My answer to a lot of different things, which is like, you know, I can't fix this. Could I make it look better? I mean, I do calligraphy as well. And that's a principle of calligraphy, is when you make a mistake, you turn it into something interesting.
Right.
That's the whole job.
I like it. It's like all of a sudden there's a flower there on that P. Like,
yeah. I mean, in aerospace, I'm thinking there's probably some of that too, is when you see something go wrong, God forbid, you don't want it to happen on the real thing. But you use it as
I think I mentioned earlier that, you know, we have rip stops built in so that we do anticipate we could get a tear on orbit too. And as long as it doesn't keep on going, you know, we want it to stop, and so that's all been anticipated. You know, don't want it to happen, but we try to prepare for it.
And plus, another really great thing, I mean, whatever you're doing in STEM, whatever you're doing in life, just because something didn't work perfectly right the first time doesn't mean you throw up your hands and give up, right? James Webb goes through it, and they fold the sunshade, and they unfold it, and they learn from it. If there's a tear, they're like, hey, there's a tear there. How can we address this?
We one of the reasons we test is because we want to learn.
Yep.
We hope the tests go well, and then sometimes you find something during the test. But if you don't find anything, that means you're just wonderful in designing something, and you don't need to test. But we've never done that, and I think James Webb. I know, like I said, I get back to that frustration for how long it's been. We exhaustively have tested James Webb and plan to do it, so we have much more testing because of the value of the mission, the importance of the mission, and how many years have been in the mission. We test this much more than we would a typical program.
Yeah. Absolutely. It's just, I mean, a lot of people are like, oh gosh, it tore, geez, they don't know what they're doing, or this is never going to work, or whatever. But as long as you learn from it, it doesn't matter if you're folding an Origami F14 or you're folding a sunshade for a space telescope. As long as you are doing these tests and you view it as a learning process, then you can go back and in your final product, hopefully, you just get better and better until you got something that's ready to launch, right?
Exactly.
Yeah, I like it. A couple just really quick questions here. There's so many questions, we never get to all of them, but here was one. Shar, this was for you. Are there any tools you recommend for origami? So is there like a folding thing or a special knife that you use to make creases? Or is there anything like that in origami? Never thought of it.
Yeah, there are some tools,
Yeah?
actually. One of my favorite
She's got some.
One of my favorite tools is this.
Okay.
The little paper slicer.
Okay.
So you stick the paper in here.
Yep.
It's so much better than scissors.
Wow.
If you've tried to cut along a fold with scissors, you know what I'm talking about.
Yeah.
Fold the paper lightly and you just slice it.
It's
and
like
I do a lot of
blade.
that. I do a lot of modular stuff, so I'm often cutting paper down to a size that I want.
Yep.
And so that's one of my favorite tools.
Cool.
There's things called bone folders, because originally they were made out of bone, but they can be made out of anything. And they usually have an edge that is not super sharp, so you're not going to rip your paper when you fold a piece of paper.
Yep.
You want it to be a really solid crease. Sometimes it's really hard on your hands.
Yeah.
And some people like to use a folder, especially if you're using thicker paper.
Yep.
And so a bone folder, which, as I said, could be made out of wood or plastic, it is rounded just a little bit so that it doesn't rip your paper. I have used old credit cards for that purpose, but you have to be a little careful because they're pretty sharp.
Right.
And so that's a second, maybe very popular thing. Some people like to fold super small stuff, amazingly small stuff. And they might use tweezers or a little pointed. Sometimes you use pointed objects to poke out corners.
Right.
So that you can get the effect that you want. But some people use tweezers on their really small stuff.
Yep.
We have a big Q-tip, by the way. So we called it a Q-tip because it was like a big long pole with a soft thing, and the technicians would sort of use it to push the sun shield, just push it a little bit to get it to go in the right. We called it a Q-tip because that's what it kind of looked like. It looked like
when you get it, like you get a crimp in something, and it doesn't want to totally fold out to the corner, right?
Yep.
You could use something like that, something not so pointy that it's going to rip right through your paper.
Right.
But that's really interesting that you have that same technique.
Oh yeah. Real rocket science when you see this.
When you see this big Q-tip.
I mean, if you want stuff to stay folded, so I know somebody who puts pleats in fabric.
Okay.
And so her tool is an iron, a really hot iron.
Right.
And what you're doing is you're breaking the fibers and you're giving the fabric permanent memory.
Oh.
I mean, basically, when you fold a piece of paper, it has memory and it's not really going to unfold.
Sure. It's always got the crease in it.
Yeah.
Like yours, like your sunshade that you keep holding up.
My paper sunshade. That's why we don't make it out of paper.
But you can give fabric permanent paper or permanent memory too. If it's not, like, natural fabrics don't like to do that, but synthetic fabrics can be just melted at the edge a little bit. God. So you've seen maybe I have a scarf that has this same thing like embedded in the whole scarf. And I'm pretty sure it's made that way. It's made with 2 pieces of paper with the fabric sandwiched in between, and then it's folded up and it's put under high heat. Now, maybe not an iron. I know sometimes the person I was talking about, her name is Win-Win, and she does a lot of sort of fashion origami.
Yeah.
And she'll bake it in her oven.
Bakes it in the oven. Nice.
But, it's a technique to give something a permanent, a permanent crease in it.
Permanent crease. I mean, I love it. It doesn't matter if you're doing spacecraft engineering or you're doing fabric, fashion creasing, or you're folding origami. I mean, a lot of the same principles, whether it's a mathematical reason that peaks will collapse or not, or just tricks that you can use. It's all about learning. And we've learned all these different things because we got to talk to y'all today about James Webb and about origami and little tips and tricks. And then earlier with Alicia when we were folding that F-14 Tomcat, I'm gonna have to go back to the beginning of the stream and actually try to fold my F-14 Tomcat. I tried to make something, but it had tape on it, and I didn't want to show Char, so I threw it over there so she wouldn't see it.
I'm not that much of a purist.
Well, let's. I know we always have so many great questions. We never have time to get everything in there. Let me do this. Let's pull Summer back over here with us because we are coming up on the end of our time. We do 2 hours, and when we first started these events, Intrepid was like, 2 hours? What are you going to talk about for 2 hours? And every event we run out of time. We never have enough time to get through all the questions and everything. But Summer, welcome back. Thank you so much for joining us here today.
I ran and did a costume change because I forgot I have a Lagrange point necklace.
Oh, look at that. Yes. There's by the way, there's 5 of them.
Yeah, this is just 1 and 2.
Yeah. A Lagrange point necklace, and you have the James Webb earrings there.
Okay, we're going to have to talk after the show.
But I also wanted to show you you talked about fashion, but we also mentioned Jiffy Pop.
Oh, hey.
It's very much like the star shade.
That's right.
It is true.
And then
I said
awesome.
I wanted to pop one of those live on the stream, and then I completely forgot about that idea. You got a Jiffy Pop that's actually folded up.
You can still buy Jiffy Pop. I have to check that out.
Oh, y'all. So again, Summer Ash is our moderator through the main part of the conversation there. Summer, thank you so much for the time today. Keith Parrish, look, we'll Brady Bunch it, right? Keith Parrish with the James Webb Space Telescope. Keith, thank you so much for the time today.
It was a lot of fun. I really enjoy talking to everybody about James Webb. It's everybody's telescope, so hopefully everybody will be as excited as NASA and the astronomy community is. Yeah,
it's so cool that it's such a big international effort from so many different places coming together. Like you said, no one organization could put it together. But we're glad that out of all those organizations, we had you here on the stream today.
It was a lot of fun. Thank you. It was a pleasure.
Excellent. And then also, last but not least, Charlene Morrow with OrigamiUSA. Charlene, thank you so much for the time today.
Totally welcome.
Yeah, very cool.
I love hearing about these connections between things.
Yeah, it's cool.
It's really great.
Absolutely. Did you ever think that you would have been sitting here talking with a spacecraft engineer about origami?
No, a friend of mine said, "Oh, I didn't know you had a career as a aerospace engineer." It's a little intimidating, but a lot of fun.
Excellent. So again, everyone here, chat, y'all know what to do. Put some thank yous into chat over there for everybody that makes these things, these streams happen today. Especially, let me do this real quick. Intrepid Museum's Virtual Astronomy Live is made possible by the New York State Council on the Arts with the support of Governor Andrew Cuomo and the New York State Legislature. So Virtual Astronomy Live is also generously supported by the New York Space Grant Consortium. We are doing these things every month now. We get new topics, we get new guests, and every month we're going to have another Virtual Astronomy Live. That is because we've got some grants, educational grants. We've got some money to actually make these things happen. So massive thanks to the people who financially support this, making this happen. And speaking of that, there's going to be more shows coming up. The next monthly Virtual Astronomy Live will be on Thursday, July 16th. So check this out. I got a slide. We actually have the date a month in advance. Thursday, July 16th, we're going to be talking about astronaut photography and art. So for more information, you can go over to Intrepid Museum. We'll put that link in chat there, and y'all can actually sign up for reminders and stuff like that. But we're looking at doing these through the rest of the year, the Virtual Astronomy Live. So I hope that y'all are enjoying them for sure. That is the end of our time here today. Again, Summer, Keith, Charlene, thank y'all so much for the time. Yeah. It's a fantastic time being able to hang out with y'all here virtually. So we really appreciate it.
It's a lot of fun.
Yeah, all right, so now we can all awkwardly wave goodbye. And we'll say later, nerds. Everybody watching, thank y'all so much for joining us here again, Intrepid Museum's Virtual Astronomy Live, and we will see y'all next month.
Thank you.